So let's take a look at the Biot Savart Law. This is a useful law for calculating B from current. Just to remind you who Biot is, he was a French physicist. He worked on optics and he also worked on magnetism. He went up in a hot air balloon with his fellow physicist Gay-Lussac. Savart was a French professor at the Collège de France and he collaborated with Biot. The thing that they did was basically try to understand from experiment how B fields were generated and what were the relationships which gave you a certain B field from a given current. And this was done, of course, very early. Look at the dates for their lifetimes, and they're not in the form that we're going to present, but nevertheless they figured out the basic rules. Biot Savart tells us how to calculate B from steady state currents. So these are constant currents that aren't changing, and remember, a steady current is a flow of charge that has been going on forever, and it will be going on forever. The currents produce magnetic fields that are constant in time. For such currents, the charge density within the conductor carrying the current does not change, and that's equivalent to our divergence of J equaling 0. Let's imagine that we have a loop of current. In this case here, the current is traveling in this direction here. Display the various vectors that are involved. This is somewhat similar to looking at electric charge. And what we have here is a origin right here. There's the source vector r prime, which comes up now, instead of a charge, it comes up to a little element of current. Here I just show you the vector dl. And if you wanted to relate this to a current times a distance, you would take IDL. The field point P is at the vector r. And remember, we had our funny vector, which is equal to r minus r prime. And so that's our delta r, which is right here. So basically what that is that you've got some little current here, and it's the vector between that little current and the position of the field point where you're trying to determine the field. So dl prime, let's put a prime on this, is a element of displacement along the wire. Our funny r is the vector from the source point to the field point. Bs can be written first in the form of the differential dB at P in terms of I and the differential dl along the current path. And that dl is located at r prime. So here's the law. This is saying that the differential of B due to this current element is equal to I dl prime cross r funny r divided by r cubed. And then it has the constants mu 0 over 4 pi. Mu 0 is the permeability of free space, and it has units newtons per amp squared. The units of B, if you just take and substitute in the units for all of these things here, would be newtons divided by ampere meters. You can get that easiest from just looking at this equation here, putting in coulombs, putting in the velocity, which is meters per second, and then figure out B in terms of newtons. One of these, 1 newton per ampere meter, is equal to a Tesla. And this is the most common unit for B. Let's go through this again. If you look at then the equation that I gave you for dB, it's quite common to take 1r here, divide it into r vector, and that gives you the unit vector in the funny r direction. So then we reduce that to a square. So that's basically the same law, just simplified a little bit for some applications. To find B due to the entire loop, we integrate dB around the loop. So dl are small vectors pointing along the curve C in the direction of current flow. So to find the B, we integrate over the loop, and notice that this vector here, we're treating I as a vector, can be written as the magnitude of I times the magnitude of dl prime. We do this all the time, and it's because the direction of I and the direction of dl prime are equal. So doing that, then we can change our B into an integral, so we're getting the entire B field, and we can bring out mu 0 over 4 pi, and then we can put current I dl prime into the integrand if we wish. So this would be the current times the unit vector in the direction of I. So remember that this dl prime is an element of displacement along the wire. It's associated basically with the direction of current flow at a particular position, and funny r is the vector from the source point to the field point. So let's take a look at the simplest example, and that is the magnetic field for an infinite straight line. So we have a straight line of infinite length carrying a steady current, and it's stretched along, let's say, the x-axis. And what we want to do is find the B field at a point here, which is a distance s from the wire. We start with our equation for dB, and we may use r hat, I can't remember, but we'll see. So we do the usual simplification, and that is we let r be equal to funny r, which is equal to this quantity here. So in other words, it's the distance from an element of current to the field point. We're just going to call that r. The source point is at some value of x. We could pick any place on this wire as an origin. It doesn't matter. So this could be an x, it could be 0, whatever you wish. And we just simply let x equal to x prime, which is the source point. The other thing to notice is that if you take any little dx on that wire, that's equal to dl, because they're both in the same direction, which is the direction of the current. Doing that, then, we can, and by the way, this could be a prime. If we substitute that in to our dB equation and switch to an r hat vector instead of the funny r, then we'll have the dB equaling to this relationship here. Now, if you have the situation that we have here, and you take a look at the dx cross r hat, let me put a hat on this one just to keep it consistent, then don't put that there, because we're going to use dx cross r. If you look at the direction of dB due to r and dx, so you take dx in this direction, cross it into r, then if you use the right hand rule for the cross product, the B field will be coming out of the page here. So that gives us the direction of B. Now just imagine that you're taking this element and just moving it here. Everything's the same. You'll still end up with the B field coming out. dB is out of the page, and when we integrate, we're going to have a vector coming out of the page. So remember, for the cross product, when we take the cross product, the magnitude of this, so if I put magnitude here, is equal to r dx times sine of theta. Theta is between the vector dx and the vector r. So we're going to use that. Let's express r in terms of s and x, and so if you look at the triangle that we had on the previous slide, you'd have r squared equals s squared plus x squared. So you can solve for r. The cross product gives us the factor sine of theta, but let's express that in terms of s and r, s and x, and so this would be s over r. Put in r equaling this quantity here, and so you end up with the sine of theta given by this expression here. If you come back to dB, which is written here, and we've taken cross products, so the magnitude is equal to, has the sine theta in it, then if you substitute in the sine of theta, which is right here, and you substitute in r squared, which is right here, then simplify, and this is dB. So it has the factor mu 0 I over 4 pi, has an s here, s squared plus x squared, and so on. What we want to do is integrate this from minus infinity to plus infinity in order to get the b, and this will be the magnitude again, setting up the equation where we bring out all the non-x factors that we can. That's this prefactor here, and so we're left with this integral here. Well, you can look it up in tables, maybe you've memorized it, but in terms of doing this by Mathematica, one finds that this integral reduces to this quantity here. Putting that in then for the value of b, we get the prefactor times 2 over s squared. 1s will cancel 1s down here, and so we'll have mu 0 I over 2 pi s. This is at the point P, and if we look at the direction again, this is out of the page. So the vector B is coming out of the page. This is a classic equation for the infinitely long wire. I repeated the equation for B here, and the thing that you might be interested in is that the E field from a charged wire also has this 1 over s behavior. So what is the direction of B? Remember what we had before. This is dB in terms of these vectors. So what you're interested in is how does the product of the vector product of dx with r change if you were to take this point and move it around this circle here. And what you find is that it doesn't change. The magnitude of the B field stays the same on a circle here. The direction of B changes. What you have then is, if you find out what that is, then dB is tangent to this circle here. So if you take dx cross r, for r pointing to the circle at different places, you always find that dB is tangent to this circle. What it means is that if you, at the current flowing in this direction, then what you have at the top, as we had before in the diagram, it's coming out of the page. If you're down here, right here, it's into the page, and everywhere else it forms a tangent to this circle here. And so this is an example of what does the B field look like, and the contours of the B field are these circles. And of course the magnitude decreases as you go out to larger s. The way we get this pattern here is use the right hand rule. So for a straight wire, you put your thumb in the direction of the current flow, you wrap your fingers around with your right hand around the wire, and your fingers point in the direction of B. So your fingers would basically go around there like this. They are pointing around the wire and gives you that circular form of the contours. What happens if we take a finite wire? So here we're going to go from minus L to plus L. So we're not taking an infinite wire. And so we've got the same point, a distance s, from the wire, but we have a finite length. Turns out, if you look at it here, that the dB is the same. Here's your dx right here, and the r and the theta and s and so on are all the same. We can use the same integral. Looking at the symmetry of the two cases, we basically have the same kind of idea that we're going to integrate from one point on this side to another point over here. Before, we let those be infinity, but here we're going to stop it. So that means that the magnitude of B is determined by integrating x from minus L to L. So if you do that, all you do is change this limit here and this limit here to plus minus L, and do that integral. If we use Mathematica, we can do this very quickly, or you can look it up in a table. And this integral here, which is the factor that we have here, is equal to this quantity here. You'll notice that you have s squared down here, and since we're now going to multiply by an s, that will simplify to this final equation here. So we have, for a finite wire, we have L dependence and we have S dependence as given here. If you look at a point where you're in the region close to the y-axis like we have here, then the field coming out of here will be given by the right hand rule. If you're here, right hand rule. If you're here, right hand rule. As you get closer and closer to the ends, the field lines are not going to give you the symmetry that you have here. But as long as you stay close to the middle, you'll have circles coming around the wire. For points in and near the YZ plane, which is this plane here, YZ plane, the right hand rule applies. So as long as we stay in this region. Let's take a look at a circular loop. So we have a circular conducting loop, say of wire, of radius a in the XY plane. This time I put the coordinates like you see here. And we've got a steady current flowing in this loop, and we want to find B along the symmetry axis. So we put our point P on the z-axis as we show here. Look at this b then. We have the same equations. These are the same two equations that I gave you before. In this case here, dl prime is a vector like I've shown here, which I'm going to call du. So that's the tangent vector that's in the direction of the current flow. We'll pick the point A to be where we're discussing the vectors that will give us the field. Now realize if I move it over here, I could just rotate the y-x axes to correspond to a picture like this. So here's our radius A, here's the origin, here's our current, and here is the r vector, which is, remember, it's from the source point to the field point. So this is our funny r, which we're just calling r. If we take the vector du and cross it into r, notice that they're at right angles. And so the magnitude of du cross r is down here is in fact equal to r du. And that comes about because of this 90-degree angle between these two. Why? Because the circle is in the y-x plane. The r vector is in the y-z plane. So those have to be normal to each other. If you take the point chosen, this point A, it is at an angle theta with respect to the y-axis. If you wanted to find a different point on this curve and do the same problem, the length of r would not change, and of course du would not change. It would just change direction. And like I said before, you can always switch x and y axes. You can rotate them to get to the point on the circle that you wish. If we look at two points that are opposite to each other and look at the resulting field, what you find is that the dBz doesn't change in terms of being non-zero. This is dB here. But the dBy rotates with the point A as you go around the circle. If you consider then that you go all the way around, all the components of dBy add up to 0. And so you always have an opposite vector in the y direction that corresponds to points that are opposite to each other on the circle, but they both add dBz direction. So here I show you the relationship between the vector dB and their components. And if you look carefully at the angles that have right angles and so on, remember dB has to be perpendicular to r and du. Then what you can see is that this angle here, in fact, is theta. Remember again, this has to be perpendicular to r, and so that's going to end up having the same angle as you have here. Let's go back to our dB then and form it. Because of the relationship between the length of b and the projections, we're interested in this quantity here, and so that's going to be in magnitude the magnitude of dB times the cosine theta. So you're using basically this triangle here. So this will be the cosine of theta times dB, and that's what we have here. The cosine theta is going to be equal to, I didn't do it yet. So this is dB right here, and that's by just evaluating the equations here with all the right angles that you can put in. And cosine theta is equal to a over a squared plus z squared to the 1/2. Where did I get that? I get that in this triangle right here. We have a up here, we have z here, and so r is equal to, basically r squared is equal to a squared plus z squared. Cosine theta is equal to a times, and so that's where we get this. So putting that into dBz, we're going to have the prefactor here, and then we have the same du over a squared plus z squared here, and then we have cosine theta here. Simplifying that gives us the factor, or the exponent 3/2 right here. Remember that we've got du, this little tangential vector on the circumference or along the circuit that we're interested in. I called it C. So looking down on that, just looking at the circle, so we're looking down the z-axis, then the magnitude of du is just simply the radius and the d phi. So right here du is equal to a times d phi. So we can put that in. So down here I've got it again. du is 80 phi. So we substitute in for du, and now we have everything in terms of z and the angle phi. It's kind of amazing, but what we end up with is everything remains in the equation except the integral over phi. So we have a d phi. There's no phi dependence, so we just get a 2 pi. If you simplify everything, then what you have here is that b of z is equal to mu 0 I a squared over 2 times the 3/2 power of this would be r squared. So this is the equation that we want for the B field at a distance z from the center of the circle. So it's along the symmetry axis here. It's the only component, and so you could put vectors on here. You could put a vector here and just put in z hat for the direction. What happens if we go far, far away? Well, it's just simply z gets so large that you can throw this away, and so you combine the z squared with the exponent 3/2, and you end up with z to the third. If you remember the dipole field of a charged dipole, it had a distance dependence of z cubed, and it turns out that this coil, or this circular current loop, is equivalent to a dipole, a magnetic dipole, that's pointing along the axis. And what we're doing is we're looking at the field of that dipole as we go right up the direction of the dipole, and that depends on z as 1 over z cubed. We're going to talk about the field of a dipole later. I just wanted to point that out. Having done the circle, it's possible to use the approach to look at the field at the center of an arc. So this is a circular arc that has finite extent. Phi is the angle that subtends this arc, and we'll let P be at the center of this, and we'll let A be the distance to the arc from point P. Now there's a lack of symmetry here, so that we're only going to worry about the point that's in the plane of the circle. So in other words, points along here and this point here define a plane. And so we're only going to be at the center of this. Why? Because the symmetry isn't sufficient to get the field at some point other than this one. It can be done numerically, by the way. We're going to need a vector from the source, which is a point on this curve here, to the field point here. So this is our funny r, which we call r here. And here's our little element of displacement along the direction of the current. And we use the same argument. du is perpendicular to r, so that simplifies the relationship in terms of the length of du cross r is just dur. And we're going to let the magnitude of r be constant, which is equal to a. If we put that in to our equation here, then dB at P from this little differential du times I, and so any du is on the arc, will be out of the page in terms of direction. So this is similar to the circular arc, except it holds for this partial arc. So the field due to these little du's will be out of the page at the point P. The magnitude of dB will be given by mu 0 I over 4 pi a squared du, and that comes about by just putting in the vectors here. These are perpendicular to each other, and then using the same relationship for du and d phi. So we put that in here, and we're left then with the B magnitude at the point P is equal to this quantity here, integrated from 0 to phi and over d phi. We get a very simple equation. We get this prefactor just times the angle phi. The direction at P, I've said, is out of the page, but if you pretend that this is almost straight and do the right hand rule, you can see that your fingers are pointing out of the page. So any partial arc can be done in this form, as long as you're staying in the plane of partial arc. So here's the same equations up here, and let's ask the question, if we let the upper angle phi go all the way to 2 pi. So we're going to integrate the partial arc. We're just going to keep going And so we will go all the way around. We will get the field at the center of a circular circuit just by letting that angle go to 0 to 2 pi. We just set that equal to 2 pi. And so that's right over here. Here's our 2 pi doing the integral over phi. And so what happens is that this simplifies to this equation here. So this is b to an entire circle at the center of the circle. But we did this problem here, where we found the field here due to the circle. If we want to find the field right here, we just set z equal to 0. So go back to the equation that we derived, which is right here for b of z. So that's out here at p. And we just let z equal 0. And so if you do that, you can see that this simplifies. The z basically disappears here, so we're left with this. And if you simplify it, you get the same result that we got up here. So taking a partial arc and going all the way around, or taking our z-dependent b and letting z equal 0 gives us the same results. I want to go back to the circular current loop where we have the z-dependence. And I plotted it here. So what I have here is b of z versus z, and this is the exact equation. There's no approximations here. And this is what it looks like. So if you're at the center of the circle and you start away, you'll notice that it's not linear at all. It looks linear, but it really isn't in this part here. And then you see this very slow decay in the strength of the B field. I've set all the parameters equal to 1 in our equation, so the only thing that's left is this 2 here. If you make this one, and this one, you'll end up with a half, and that's what we have here. As you go out here to large z, remember what we said it looked like was this 1 over z cubed. You can't see it, but that's how this is falling here. As a function of z, then, you can see here this is the value of the a. This is a equals 1. So that's how much field you have if you're 1 radius of the circle away from the center, and then so on. This curve here is very important in terms of some applications. And I'll only mention that sometimes you take 2 coils like this in such a way that either you run currents to get a point right in the center, which would be on the z-axis, so like that. It's on the z-axis of each point. You run the current such that the field is 0, or you run the current so that you get a non-zero value, and what we will find is that in the vicinity of this point the field is fairly constant. These are called Helmholtz coils. This curve here gives you the z-dependence of 1 coil. So you take 2 of these in the right positions and you get the field right in the center. Let's look at the forces between 2 parallel wires. We'll consider the force of attraction between parallel wires, and these are infinite long and they're a distance d apart, and they have the currents I1 and I2 as shown. So this is wire 1, this is wire 2. We're going to find the force on the wire 2 due to the wire 1. We could do it the other way if we wish, but this is the way we'll do it. The field for a point on 2 due to the entire 1, so we're using the infinite length wire, will give us a force. That force will be equal to I2 times the integral of dl along the wire 2 times the b due to 1. And this is where we use the infinite wire results. The magnitude of the force on 2 due to the current in 1 is equal to, okay, it's b due to 1 times I2 times the integral of dl along 2. So basically what we're finding is the df on a little element of this and then integrating over the length. So when you do that, you end up with mu 0 I1 over 2 pi d, that's the distance, times I2 times the integral of dl along 2. Now wait a minute, this is an infinite wire. This is infinite. We can't do this problem. Well, we can. Integral is infinite, but we can do the force per unit length. We've done this before with electric charge. If you want per unit length, you take this force, divide by the length, so you're basically This is the length, by the way. Then you get rid of this part of the integral, and you're left with just this factor right here, which is what I've shown here. This is the force per unit length between two parallel wires of infinite extent, and the separation is important because as you make them farther and farther apart, the force goes down. Obviously, if you put bigger currents through each wire or one wire, you'll have a bigger force per unit length. The way we've got this, you should look at the direction of the force. Remember that we have a cross product between what you might call V cross B. In this case here, it's V2 and this is B1. So you use your right hand rule on I1, and that gives you a field here into the page. So that's into the page. Let me represent that like this. So that's our B due to I1. Okay, what direction is V2? Well, it's in the direction of current, so this is V2 right here. So V2 and this is B1. Take the cross product, so which way is it? Well, if you take V cross B, it gives you a vector in this direction. If you have the currents flowing in the same direction, they attract. Remember, I didn't mention that. Whatever you do over here is being done over here too. This field will put a force on this wire. This field, due to this current, will put a force here. So basically what you have then are forces that cause attraction between the two wires. If you switch the direction of the current, then you go through the same analysis, and so you'll see that the wires repel. Next time we'll take a look at the second standard equations for determining B field, and that's going to be via Ampere's law.